Good morning. Hello, everyone. I hope you're all awake. Hi, Keon. Thanks as always. Hello, good morning, everyone. See you. So I hear a little bit of background noise. I'm just going to temporarily mute you, and it's only temporary. Um, if at any point you need to unmute, please do so. It's totally fine. Let me open my chat because I see all this is this is what I look forward to on Zoom when I see all the good mornings in the chat. So good morning, Amir. Good morning, Sanjita. Good morning, Saja. Good morning, Robin, Brian, Luis, Hofset, John, Nate. John, good to see you too. Owen, good morning. Azure, good morning. Oh my gosh, everyone. Alexandra, and I talked to you yesterday. And hi, Neil. I see the clap too. And good morning, Henry, Daniel, Nathan, Bradley, Esmeralda. Good morning to you all. Welcome back. Noah, good morning. Um, we made it to day two, just a few more days. So, day two on winter is like week two in during the semester. So, um, it's good. We're all here. So I'll start with two announcements just before we get started. And the first is that we have many new people today, and I welcome all the new people today. I'm glad to have you. What you want to do to get started, if this is your first day, is to take a tour of Canvas and you want to watch the recording from yesterday. There are many things we talked about yesterday. I think we went way over on the intro. So if you have any questions about, the grading, the syllabus, all of it is in the recording, and um, hopefully you'll feel caught up. But it's not like you're too far behind. I actually posted the wrong syllabus yesterday, so it's all good. As long as you made it here, it's a good thing. Um, yeah, so for anyone new, please look at the recording from yesterday, and then if you have any questions, let me know. um, yeah, I think that's the main one for anyone joining today. Let's see, our second one, let me tell you a little bit about our agenda today. We are going to finish chapter one. We're going to continue where we ended yesterday. After we finish chapter one, we are going to take a tour of our Canvas page. And from our Canvas page, I'll show you the homework and the lab that is associated with chapter one and that is due on Friday. So we'll do that. And then I think we'll take a break. We'll probably need like a 10-minute break. And after the break, we'll come back and go straight into chapter two. I'm not sure if we'll finish chapter two. We'll see where it goes. Either way, at 12:30 we stop. No matter what happens, at 12:30 I hit stop recording. um, yeah, so let me put it out there for you guys. If anyone, does anyone have any questions
I
that
do.
one? Okay, Randy. Hello, good morning. Before we start.
So my questions are from chapter one. There's two of them,
Mhm. Are
and so
they are they homework related?
they're not homework related. They're just I was reading and I kind of didn't understand one or two things. So the
Yeah.
first one is on dimensional analysis. The
Uh-huh.
symbol, it appears to be a partially finished infinity sign, and I just wasn't sure if that was the book cutting it off or if that was the actual sign.
That's a good question. So first, I'll say that that symbol that you see, you might see it today. Everyone will see it today. That means proportional to, and it looks like that little Jesus fish you see
Like
on
a
cars
stick.
sometimes. Yeah, that symbol means proportional to, and it means that there's a physical relationship. So if something gets bigger and it's proportional to that, that other thing also gets bigger, but not at the exact same number rate, but in relationship to it. Um, yeah. Second question.
And the order of magnitude, like, so it was the second step that says that the multiplier is less than the square root of 10.
Hmm.
The order of magnitude is the number, is the power of 10, or the order of magnitude of the number is the power of 10 in the scientific notation. If the multiplier is greater than that square root of 10, the order of magnitude is one larger. And so like I didn't really understand what that meant at all. And I understood the application. Like if it's four blah blah blah, you like you make it 10 to the power of one. And if it's like 3.2, it's 10 to the power of zero. And
I,
that's for
I don't
estimation.
I don't think I quite understand the question either. It's also something we haven't covered yet. So perhaps we could do this one in detail, maybe you and I. Yeah, I'll actually, if when we go over this, I think I'll keep the record button on in case I'll keep the recording on in case anyone has a question. But I think the question is if it's less than 10, is it 10 to the 1?
Well, like, what does exactly the order of magnitude mean? I get that if
Yeah.
it's like it's
Yeah,
10
so,
to the
so
power of
Randy,
one.
Randy, we haven't gone over that. So this is why you would have a question. But in summary, an order of magnitude is an estimate. So you'll never
Okay.
have, yeah, you'll never have an exact value or an exact answer. It's really, you know, how do you make things easy to talk about quickly when you don't have a piece of paper with an exact number or a calculator? So, you know, instead of me telling you to count 989 pennies, I might say count 1,000 pennies, and that's an order of magnitude estimation. Yeah.
Okay. The
Okay.
example made it make sense, but the text was confusing.
Yeah, that square root of 10, that throws me off too. So I need to like wake up a little bit more. I've only had half a coffee, so I think once I finish this bad boy at the end of class, I think I can help you in with
Okay.
exactness. Yeah. Um, any other questions from anyone before we start? I'm happy to hear. Yes, Nate, I also need some coffee. And good morning also to Patricia, Daniela, Andrea, everyone there. Okay.
As a class today, but I don't have in the class in Canvas. I think it take about 24 hours. So for the all the homework and all this assignment, it will be
Hi, Nada. I can't actually hear the ending of your question because of the signal, but you just added the course, and so you will one Canvas will appear, you know, like you said, in the 24 hours. But anything else, you'll have to email me until it catches up. Yeah, I'll also show everything on the screen. So for anyone who is new to the class, you want to screenshot and write down as much as possible for things that you're missing because you're not enrolled in Canvas. And any of those like very individual situations I can help with and kind of make sure you get through it through email, or at the end of class today, we can talk about it just to make sure that you got everything you need. And again, feel free to like um, feel free to stay after if you didn't get what you need. I'm happy to give it to you. Any other questions out there? Okay, and again, for our new people, I can see everything on the screen. So if you want to use the chat, use reactions, you know, turn on a video, unmute, feel free to do it at any time. Um, yeah, I can see it, and I'll set up so that I can see everything you're doing. Okay, so I guess we're good to go. Anyone else? No? Okay, let me set up my screen to start us off with our, to start us off where we finished yesterday. And nicely, I'll give you a little, this is a little reminder. Okay, let me share my screen and then give me a second to rearrange a little. Okay, and let me find the chat box. Okay, I can see the chat. And I'm about to block my other screen with your windows, and I can still see you guys. All right, so I can see you all again. Any reactions you want to use, it's very helpful, especially if you're kind of just good to go and don't have any questions. You know, you can let me know through reactions too. Okay, I think I am completely ready. And so what you should see on the screen is one of the beginning slides from yesterday. And so our chapter one is a major introduction into the world of physics as a whole. It's not one topic just yet, but as a whole, what is it that we're going to see in physics? And before we start looking at a specific topic in physics, Physics 101 will be all about motion. We really have to set up the language of physics. And what I mentioned yesterday was that our goal in this class is to describe something physically and support it mathematically. We always want to do both, and we should always be able to do both. So if you ever see me have a question about something or you have a question, we're going to try to prove it in both ways. That's how we know we're right. Okay, so to set up our language for physics, we're going to start with what are the fundamental quantities of physics. And yesterday we went over length, mass, and time. And these are three of the four fundamental quantities. The fourth one will come in Physics 102. And if you want to know it, watch the recording from yesterday. That's the sneak preview. Okay, so for our units, we established some parameters. Any type of unit or that describes a physical measurement must be readily accessible by everyone. It must have some property that can be measured reliably by everyone. It must yield the same result by everyone, no matter how it's measured, and it cannot change over time. So, for example, you guys seem like you can't use glass to as a form of measurement or as a reference, because you've ever seen those church windows, the European church windows with glass, they kind of melt, right? So glass moves over time. So we could never use glass as a material because it's not stable enough. So here's what we came up with. The fundamental quantities are length, mass, and time. And these are the three sets of units that you saw yesterday. And let me highlight the most important part of knowing the fundamental quantities of length, mass, and time is the unit. So for length, we will always use the meter. These are SI units, right? SI units, we will always use the meter. For anything that has to do with mass, we will always use the kilogram. So not just the gram, but the kilogram, a kilogram. And anything that has to do with time, we will always use the second. So notice that in every single one of these tables, you will always see the unit right next to it. Anything that includes a physical description must include some sort of mention to the unit. So a graph will always have units right next to it. A table will always have units right next to it. Um, it's something that we kind of take for granted because you talk about how far you're going, how long something takes, but it needs to be there. It's scientifically correct. And so this tells us about the physical nature of something, but it doesn't tell us about how big or small something is. How big or small something is the number that you see next to it, right? And then in our scientific world, we additionally are able to describe how big or small something is with this type of notation next to it. So this is what we call scientific notation, and it's kind of a shortcut for us to write small numbers in an easy way and big numbers in an easy way. So this is what we finished with yesterday. So um, all of these fundamental quantities will describe the physical nature, but these units right here, the numbers, will describe the magnitude. I'll write it right here. And for this week, and probably for next week too, knowing the difference or knowing really what the magnitude of something is huge. You want to know that the magnitude simply describes a number. It does not describe anything in forms of direction. It only describes how intense something is. So notice that this magnitude, you do not see any type of physical description here. You do not see meters, seconds, or kilograms. You only see numbers. And we see three different ways to describe these numbers. You've got to know these by name. When we use scientific notation or the power symbol, this is when you see the 10 to the exponent. When we say prefix, you want to write out the nickname. It's kind of like a nickname, right? And when you see the abbreviation or symbol, this is also symbol notation. And this is probably what you're most used to. You'll see the letter. Each one of these are equivalent to each other. you can write one instead of the other. So you could write 1 times 10 to the negative 3 meters will be the same as 1 times 10 to the negative 3 millimeters will be the same as 1 times 10 to the negative 3 mm. M for the milli and M for the meter. So these are all equivalent to each other, and you cannot write them together because they are equivalent to each other. It would be like a repeat. Um, so this as a whole will help us describe a physical quantity of something. We'll know what the nature of the measurement that you're making is, and we'll know how big or small it is. So let's go to the actual slide where we finished yesterday. So this is also a grand summary of the powers of 10 that we will need. And these again are the second type of units that describe what it is we're measuring. The ones you want to know, again, are these that I boxed. You want to know these like by memory, and some of them you probably know already, like centimeter, right? Or millimeter. And some of us might even know nano and micro, or you may have even heard of nanotechnology. Anything in nanotechnology means that you're dealing with physical components that are small, 10 to the negative 9, and that magnitude. The other ones you want to know are going the the the, the other way, right? We're going up now. And these we kind of know too. 10 to the 3 is kilo. So when I say kilograms, I mean 10 to the 3 grams. Mega is the big M. Think about mega millions, right? That's where that million comes from. 10 to the 6 is 1 million. Giga you might know because of your storage, your components, right? Like gigabytes, and same with terabytes. This is where it all comes from. It describes that number, and you'll see, right? The tera describes how big it is, and let's say you put the bytes next to it. Bytes is a big B, right? I think millibyte, kilobytes. I think it's a big B. Actually, I'm not
Yeah.
sure.
I
Bytes
think it
is a
is.
big B, bits is a small b.
Oh wow, Keon. Okay. Okay, so bytes is a big B and gigabits would be a little b. Okay. Okay, something to remember. Um Thanks, guys. And I think I heard Randy out there also telling us. So yeah, this is again what describes that number. These you want to know again by memory, and if you don't know them by memory, quite in the next 2-3 weeks or so, keep writing them down. It'll become common language for you the next few semesters and probably throughout college. Especially if you're a chemist, you're going to work in micro and milli. If you're an engineer, you're going to work a lot with kilo, sometimes even mega, things like that. Oh, and then Daniel has a good question. Is there a prefix for 10 to the 2? I'm certain there is. Is it deca? Does anyone know?
Deca.
Yeah.
Thank you, Owen. Thank you, Kian. I see you guys. I I don't even know how I remembered that. Yeah, Deca. Thank you, Jose. Yeah, I don't know how I remember that, but it came to me. um, there's a name for everything. But there's some that we use that are common, and the threes, right? Things in the threes, because after describing something in the hundreds, you don't want to go much higher. So hundreds is about 2 to 3 magnitudes, or 2 to 3 of the power of 10. So after that, yeah, you just skip. That's why we're in threes here. You could say 100 kilos is really close to being mega. So we would probably say 100 kilos, and then instead of saying 1,000 kilos, you would just say 1 mega of that. Um, and a question to me: should we memorize the ones outside of the green box as well? No, the ones inside of the green box are used often. In this class, we'll probably use kilo a lot, and we'll probably use centi a lot. In Physics 102, we're going to live in this world. Physics 102 is going to be all micro and nano. We're going to go into the negative 10 to the negative. So this in Physics 101, we're really dealing with things that we can see. So when I say you memorize them, I don't mean memorize them for an exam. I mean memorize them because you're going to need them as a science student. Yeah, you're going to need them. And pretty soon you'll be able to go back and forth with them too. conversions. So here's what I say when I mean that they're all equivalent to each other. You can write a number using either the power, the prefix, or the abbreviation. So 10 to the negative 3 meters, 10 to the negative 3 describes the magnitude of the number. The meter describes the physical dimension that we're measuring, right? So it's a length. So 10 to the negative 3 meters is equivalent to 1 millimeter. 10 to the negative 3 equals millimeter. And 1 millimeter can also be written as mm. And this is all equivalent to 0.001 meters. Notice we went 3 spaces over from the 1. 0.001 is what we call standard notation. Standard notation is writing out the number in full. So you might say to me, do I write the number fully out? And I'll say, yes, write it in standard notation. So this is what we call standard notation. Oh, and we have from Randy, Randy says he has flashcards with all of them on Quizlet. That's a great way to practice. And it's just really handy to know this. So thank you, Randy, for including that. That'll be helpful for everyone.
Oh, Professor, also, I actually have a computer that has memory in the kilobytes, actually. It's 2 kilobytes of memory on this guy. It's from 1981.
Whoa, Keon, I was close to beating that. I have an old one, what was it, 256, like
Megabytes?
Yeah.
Oh, yeah.
I have one of those.
That was like my first computer too, a compact, yeah.
Yeah. I think mine, yeah. That's so funny because now we're talking about like terabytes, and God forbid you get anything less than gigabytes, right? um, yeah, that's so funny. But now you know what those units are. That'll actually help you in your lab today. So I think that's good. Okay, so now you can describe any number, any physical number, with whatever is easiest to you, right? And so you can use this going in any direction. You can go large with the numbers. 10 to the 3 meters is also 1 kilometer, is also 1 km, and it's also equivalent to 1,000 meters. Now I'm gonna flip it on you a little bit. 1 kilogram is the same as kg, right? Or 10 to the 3 grams is the same as a kilogram. So notice that K replaces that 10 to the 3 is the same as writing out kilo, and the whole thing is equivalent to 1,000 grams. Yeah, and then we could go, physics 102 units, we'll get there. A megavolt, right? A megavolt would be written out with megavolt or a capital MV. And this capital M is pretty important because if you write the little m, you'll be in millivolts. So this is 10 to the 6 volts, and the volt is the V. And this is also equivalent to 1,000,000 volts. So you can write any number in 3 or 4 different ways using the power, the prefix, the abbreviation, or the standard notation. And all of these, of course, are your fundamental quantities of length, mass, and time. Okay, so let's see if we can practice. I hope you guys have these written down. We're gonna need them a little bit, and if you don't have them, that's okay. We'll just kind of come along and go along with it. So let's say we write out our number, right? And our number is 5,000. If you wanted to write this in scientific notation, you would use the power notation. So you would take that first digit and write the rest of the zeros with scientific notation. So you would have 5 times 10 to the 3. And so you have your digit, you have your power of 10. And if you wanted to write this in symbol notation, you would write 5 kilometers, where the K is the symbol for kilo, is the symbol for 10 to the 3, and the meter is the physical unit. This is all of these are equivalent to each other. All of them would be correct in my book. I'd be happy to correct any of these and see this number. Let's try it with you guys now. Okay, so now we have 2 gigameters. What would this be in scientific notation? What is the G? You could write
10
it
to the
in
9.
10 to the ninth.
Oh, okay. I heard 3 of you, and feel free to drop it in the chat too. Even though writing that exponent, that little hat takes a while. Just go ahead and do it. Yeah, 10 to the 9. So we would write 2 times 10 to the 9, and I would add that meter next to it, right? Thank you, Neil. I know that took effort. Okay, and then in the standard notation, we would add those zeros, those 9 zeros. And of course, we would then add our meter. there. And so as a whole, this is the standard number. Now, here is why we use this, right? We use this because of the practicality of it. I don't even, what is this? Tens, hundreds, millions, gigas? I don't know. I don't know how to say that, but 10
Billion.
Billion?
billion.
Billion.
Thank you. Gracias. I appreciate it. 2 billion meters is a lot to write out, right? You could just say 2 times 10 to the ninth, or you could say 2 gigameters and it'll work, right? Billions is kind of like our everyday use of the word. And we can go smaller, right? 7.32, and this symbol is the micrometer. And so here we would write 7.32 times 10 to the negative 6, and I would add the meter just so I know what I'm talking about. And in standard notation, we would move over 6 spaces to get that value, and so your number would be 0.00000732 meters. Now, I think you guys have taken classes where you go through these powers and how to figure out the number. Um, and I know there are rules out there, but what I want you to do is think about physically what is happening to that number. What is that number? 7.32 times 10 to the negative 6 describes something really small. So that is my clue that I need to make this a very, very small decimal. And that's why I move over to the left. There are much more formal, elegant rules to this, but you know. Okay, so now we can describe numbers big and small. We can describe physical properties. And this gets us to Randy's question. How important is it to be exact? When do we need to be exact, and when do we just need to fly off with some numbers and get a response of some sort? So here's when we can use estimates, and with estimates we can use an order of magnitude calculation. An order of magnitude tells us how close the number is in its powers of 10, right? And powers of 10 describe 1, 10, 100, 1,000, and going higher and higher. So here's kind of our example. Usually when you want to use one of these order of magnitudes, it's going to be somehow reliable within a factor of 10, a magnitude of 10. So let's say you can see how old this book is and these slides are. The number of bits of data on a typical Blu-ray disc. So let's all pull out our Blu-ray disc, and you would see this symbol, this symbol that you see here, right? Now, here you read 200 gigabytes. We have learned 200 gigabytes. Now, I'll ask you guys, whenever you buy your phones, right, your iPhones or whatever you have, and you plug it in and you buy the one that says, I'm going to get the one with 64 gigs. Does it actually have 64 gigs?
No,
No. Now,
because bits are different than bytes. There's like 8 bits, and then they do like an estimation.
yeah, they're doing some sort of estimation. And of course, there's some sort of storage that is needed by like the processing system that's in there. But do we need to know that? Do we need to know that we actually have 63.2 gigabytes versus 64? No. Do we care? No. Is someone out there going to argue for the 0.2? Probably, probably someone will. Not me, not us. Yes, and Jose says that the internal processing system will take some space. The internal memory will take some space, of course. So here is where that order of magnitude comes in, especially if you're out in the real world and you need to just make a quick calculation. There's no sense in adding up 732 plus 564. Like just round them each up to like 600 and 700 and add it up. So here's a great example of when we could use this and when does it matter. So here's a number, 0.0086 meters. Now we know our roundup rules that this 86, right? Just this 8 alone would round us up would round this one up to 1. If you're not convinced, you could round this number up to 9, and then you could write this as 0.01. 0.01 is very close to 0.0086 meters. In fact, the only difference is 0.0014 meters. So you could estimate this as 10 to the negative 2. Yeah. Owen says, hey, wait a minute. 0.75 terabytes versus 1 terabyte is kind of significant. So in that world of electronics, 200.25 terabytes matters. So perhaps we wouldn't say 1 terabyte there. Perhaps we'd even drop down from the tera to what's next, giga. Perhaps we'd even do that, right? Let's talk about 750 gigabytes instead of 1,000 gigabytes. But what's going to sell more? 1 terabyte's going to sell more, especially if you can fake argue that. Yeah, it really depends on what it is you're measuring. It completely depends on that. So this is really where we have to get comfortable with numbers. And here's another one, 0.0021. This 2 wouldn't round up, so this would stay as 0.002, which we could estimate as 10 to the negative 3, right? You could estimate this and tell someone 0.001 and not be that far off. It's kind of okay. And then another example, 720 meters. If you're storytelling, right, you could say 1,000 meters and kind of still get the same idea across. Now, if you're talking about having to walk this much, you might be like, hey, this actually matters. 720 versus 1,000 meters actually matters. So it really depends on the situation and what it is you're trying to describe. But this just gives us another tool set, another like sub level of using order of magnitude to describe what we see around us. And that's our goal in physics, to make things simple in how we describe it and how we measure it. So sometimes we'll want to be exact, and sometimes we'll want to use an order of magnitude calculation just to see if we're in the ballpark of the right number. And let me give you one last example. Eventually, we will see that the value of gravity is 9.8 meters per second squared. If you took physics 11, or if you just recognize this number as being close to 10, you can very easily estimate this as being 10 meters per second squared, and you'll always get in the same ballpark of the number. So if you need to ever just use 10, I do this all the time when I'm doing quick calculations, and I just need to know if I'm in the ballpark or if I'm doing something right. This is a way to go. 10 meters per second squared is completely valid. Yeah. So again, our goal is to find easy ways to describe things and simplify anything that we see. So now we have a way to physically describe something. We have a way to describe the magnitude of something, big or small, and we have a way of making estimates. So now we want to look at a situation and try to make some calculations.
Oh, I have one more thing to say about the blue. The reason is because like they do 2 to the power of something rather than 10 to the power of something. That's why the gigabytes and the bits are off.
Yeah, that's completely right. We also wouldn't, in everyday language or on a Blu-ray, you will never see it has 10 to the 2 gigabytes. Yeah, Owen agrees. That's why the 0.75 versus the 1. Yeah, that's a good comment. Okay, so now we want to continue to our modeling, right? Yeah, Owen got it. That's good connection, guys. So now we want to take this and try to put some physics behind everything, but we need to simplify as much as we see out there and take out only the details that we need to make a calculation. So for example, anyone out there, tell me, what do you see in the screen? How would you describe it?
The Milky Way?
Okay, we have a Milky Way.
Spiral galaxy.
Oh, okay, we have spiral galaxy. Daniel says stars. Yeah, all of that is true. Now, if I wanted to calculate how the Milky Way was moving, the galaxy, a spiral galaxy of stars, how is it moving? How would you draw that?
Counterclockwise.
Oh, okay, so counterclockwise is something like that, right? And this symbol alone should be enough for us to calculate things. And that's what we want to get towards. We want to get to looking at something and being able to model its motion without caring too much about smaller details, right? So this galaxy is incredibly large. and atoms are incredibly small, but they both will follow the same laws of physics when it comes to their motion. And that's really what's so nice about physics. The same laws of physics will describe both and all the rest of nature. As immense as a galaxy is and as small as an atom is, they both follow the laws of circular motion. That'll come in week 5. And this really tells us about some underlying unity in the universe, which unfortunately you won't see until Physics 103. On the last day of Physics 103, you'll see this, the whole idea behind string theory. But there is some grandness to physics. A law that describes how a basketball moves is the same law that describes how a rocket moves, is the same law that describes how, an asteroid is flying through space. And so in all of the above situations, we can just model the problem as a motion problem instead of drawing in, the stitches of the basketball or the flames from the rocket or the bumpiness of the asteroid. So our goal is to always create a model that'll simplify and substitute for the real world problem. And this will let us solve most problems in a simple way. And that's our goal, to be simple and be direct, always be direct. So instead of, taking 3 steps, try to do a problem in 2 steps. So our universe is incredibly complicated, but we want to describe it in a simple way. So for example, the motion of the Earth around the sun. We can do this in 2 ways. First, we want to look at the motion of the Earth around the sun. And when I draw this, here's my little Earth that's moving around the sun like this. And there it goes. It's turning, right? When I draw this, the size of the actual object will have no consequence in the analysis of its motion, meaning that the Earth orbiting around the sun is the same as an electron orbiting around the atom. They orbit in the same way, and the size won't say much to us unless we're looking at, something, I don't know, maybe the acceleration of it or something, when we're comparing things. When you're comparing things, sure. But when you're actually looking at the motion of something, the size of the actual object will have no consequence in its analysis because we are looking at the motion of it as a whole. The next rule is that any internal processes that occur in the object will have no consequence whatsoever in the calculation. So what does this mean to us? Again, if we're looking at the Earth orbiting the sun, you can draw a circle orbiting around a bigger circle, or you can even draw a dot orbiting around another dot, and you can model the situation as the Earth orbiting around the sun, or the electron orbiting around the atom, or a car moving around a ramp, a circular ramp on a freeway. What else? Like, what is this? The little, I don't know why I have this here. These fidget spinners, right? The point of a fidget spinner that's turning around some axis. They all model the same thing, and the size doesn't matter because we're looking at motion, how something is changing its position over time. And finally, these internal processes don't matter. So let's say you're drawing the Earth. It doesn't matter if you're drawing the Earth and an earthquake happens. Right? It doesn't matter if like you're drawing the Earth at the point of view of North America versus like Asia or Europe or South America or Africa. It doesn't matter. In fact, I get really good at drawing this. Well, I think I'm okay at drawing it, but some might not agree. Let's see. Boo. Does that look like the United States kind of?
Kind of looks like a fox.
What the hell? Yeah, it does look like.
Looks like a colonist, like an early colonist Thanksgiving.
Okay, well, if we were on campus.
Oh, I see it now.
Okay, thank you. If we were on campus, I'd be so much better. I'd have a blue marker and a green marker, and then you'd see it. Owen says 10 out of 10. Thank you. Sandra, I think it looks good too. And a perfect wobbly representation of the US. Thanks, Patricia. Yeah, I wonder what does this fox say? But you guys are right. It does kind of look like a fox. But, the way that you draw the Earth and the way that you draw these details, internal factors like this won't necessarily matter. So you can use really anything you want, the math that we use will still be the same. So here's an example for you guys, and let's get our thinking caps on. Let's try to answer this question, and you don't need to answer in detail, just kind of shoot out what's your thought process. You wish to find the height of a tree, but you cannot measure it directly. You stand 50 meters from the tree and you determine that a line of sight from the ground to the top of the tree makes an angle of 25 degrees with the ground. How tall is the tree? So, here we have a tree. It has a big long trunk. It has a lot of leaves, and you're standing from it wearing a purple dress and some shoes. But what you measure is 50-meter distance from the base of the tree, and you measure a line of sight that has 25 degrees here, and you are wondering how tall is the tree? Any ideas out there? I see an answer. How did you get that answer? Or anyone else? How would you do this?
Tangent of 25 equals h over, or equals 50 over h.
Yeah, we would use our tangent. Henry also says tangent. Keon gives us the answer, and Saja says use trig to solve, and also tangent. Yeah, and this is a perfect example of how our modeling can help us find any value, but we do not care if there's like a puddle on the ground here, if there's like, a bird flying, or a sun with like different clouds hanging around it. None of that will matter as long as we can simplify this down to a triangle whose base we know, and this angle from the base to the hypotenuse we know, and we need this height. And so very nicely, you all can calculate this. And SOHCAHTOA is your friend here, and I will refer to it often. So feel free to write it out all the time. Here you have a tangent opposite over adjacent. You solve for this height. You have an angle, and 23.3 meters. And so we have a magnitude, a number, and we have a physical unit, and we have a beautiful box to surround our answer. And very nicely, we've come up with what we need. Okay, let me do a quick time check and put a timer on. So I have 2 slides about dimensional analysis that I actually, it's funny that Randy asked that, because I actually planned on skipping these slides today to save us some time, because we don't use this very often, but I will show you in class how we do use dimensional analysis. And here's a way to show you it. The way that the textbook will show you is that whenever you denote a dimension, you could just talk about its physical nature, and that's another way to estimate what's happening and to make sure that all the physical components match up, not just the numbers, which is order of magnitude estimation, but that dimensionally what we're talking about also makes sense. So if I ask you for the time, you don't respond to me in meters, right? Dimensionally, that doesn't make sense. So in our textbook, you'll see that length can be written as a capital L, mass can be written as a capital M, and time can be written as a capital T. And you could put these numbers into any equation and continue solving with just a dimension and see if you get the right dimension. Now this can get a little confusing. So for example, here's an equation. X describes distance. Distance is a meter, so we'll say L. And we want to see if dimensionally this matches this equation here. 1/2 is a number, so it's a magnitude, and it does not have a physical dimension. So in dimensional analysis, numbers don't matter. We're just looking for physical relationships. A is acceleration, and we don't know this yet, so that's okay. We just need the unit. The unit of acceleration is meter per second squared. So meter is length, and seconds is time, and it's squared. So that's how you would write acceleration. And now time is capital T, seconds. So we would write capital T squared. And so here we just want to verify that these are in fact equal. And you see that the time squared cancels with the time squared. And once you solve for this X on the other side, you will get a unit of length. And so dimensionally, this makes sense. And so you'll see that here. Now, this isn't very common. In fact, this way of dimensional analysis isn't very common. What you see most people do in a lab or in research is actually use the unit. So this is what you would actually see. The length,
Uh,
yeah.
that makes sense. Like doing the homework, it was kind of confusing this way, but like usually you just check and see if the units check out, you know?
That's right. And that's why I was gonna skip this, and I will do a lot of dimensional analysis as we're solving for problems. So the X would be written as a meter, and I still use the bracket. The bracket indicates that we're doing dimensional analysis. The meter is equal to the acceleration, which is meter per second squared, and time is second squared, and all of this would be in brackets, and you would get the same answer. The meter will in fact come out as meters. And I gotta say that this is useful, and I use it the most in physics 102 when we start to multiply a lot of things together, and the equations will get very heavy. Sometimes you might miss a unit, or when you're trying to figure out what's the SI unit of the volt, this dimensional analysis will be helpful. So we'll just use it in practice a lot.
Use it a lot in chem too, like in Chem 101, Chem 102. It's like you'll have giant things where you just need to cancel out a ton of units, and that'll be the whole question.
You know, I'm remembering that, Owen, you're totally right. And so you'll get that same thing in physics 102, where we're using a lot of particle type calculations, or calculations that involve particles like you would see in physics 102. Okay, so this is just another tool in our physics box that'll help us. The last thing, now that we have, you know, ways to describe the physical nature, the magnitude of something, we can model, we can make estimations based on numbers, based on physical nature, is converting from one set of units to another, and helping us go from big to small, and helping us figure out practically what it is that we want to use. Well, before I move on, I just wanted to point out, this is the symbol that Randy was talking about earlier, or it looks like the Jesus fish. It means proportional to. So in dimensional analysis, then we don't care about the magnitude, we care about the relationship between the physical properties, and this in fact is proportional to each other.
So is that to say that like X is equal to AT, but that it's not really equal because there's a 1/2 there? It's just proportional.
Yes, that's exactly right. So
it's proportional when there's no 1/2, but it's equal if there's a 1/2.
That's exactly right. Yes.
Okay.
Yes. And again, the 1/2 just tells us it's just a number, right? Everything multiplied times 0.5. So it's just another factor in there. So we need to get comfortable with converting units, and this is super important in the US because the US wants to have its own set of units. And so we need to be able to talk with the rest of the world in SI units. Yeah, it's going to get confusing back and forth. Yeah, or freedom units, Jose. So these are common conversions that you want to know. These are the two that you want to have written down, and you know, you want to have this on your equation sheet, and you want to be able to use kind of little by little, you'll remember these. I don't remember them exactly. I remember there's like a, you know, there's a 2 and a 5 somewhere in there, and this is around 1.5. I don't know. So 1 mile is equal to 1,609 meters, and this is equal to 1.609 kilometers. And our 1 inch is about 2.54 centimeters. And it really depends on how comfortable you get with using these powers and the symbols. I suggest, in just to you know, avoid any shortcuts, I always convert everything to the base unit first, and then from the base unit I go wherever I need to go. And you'll see this in the review sheet in the homework too. Sometimes it can be really hard to go from a mile to a kilometer if you're trying to actually calculate it, or from an inch to a centimeter. But taking it to the base unit of the meter, which is the 1, right, the base unit, you can then easily recognize that going from meter to centimeter is 10 to the negative 2. Okay, so these in green you want to have somewhere just because they're useful, and the book will refer to them often. The other one that's really useful is knowing how many seconds there are in a year. You'll use that sometimes, but you know, we can also calculate it, right? How many seconds are in a minute? How many minutes are in an hour? Hour in a day? Day in a year? You can figure it out.
How many minutes in a year? Because there's a song that has it.
520.
Yeah.
That Rent song, yeah.
Yeah.
You guys are so right.
How do you measure?
I was in choir in like 6th grade. We did that song, so I never forget it.
That's totally right. Wow, I don't know why I never made that connection. You guys are totally right. Okay, maybe we'll play the song during the exam. If you haven't heard it, we'll put it up there for you guys. Okay, so how do we then use this? The point of knowing these conversions is that then we can convert any number, but we have to first make them into a ratio. So for example, let's say you are asked to convert 15 inches into centimeters. We need to go from inches to centimeters. You need to first make a ratio. And on the last slide, we saw that 1 inch is equal to 2.54 centimeters. So you want to convert that into some sort of ratio, one over the other. And the order that you write this in depends on what it is that you're solving for. We are solving for centimeters. So you want somewhere in your conversion, you want centimeters on top, right? Yeah, you want them somewhere on top. And so you make this ratio, and now you can convert 15 inches is equal to 15 inches times the ratio, and you can easily cancel these out, the inches to inches, and you'll have 38.1 centimeters. And this is the way you should do any conversion. And in our class, we probably will have conversions that take 1 or 2 steps, because many times we'll have meters over seconds. And so you might need to add another step for converting a second, right? And Daniel's asking, do we need to have exact conversions memorized? No, you don't need to have anything memorized in my class. But some of these are just useful. Yeah, but no, you don't need to have anything memorized. I don't have anything memorized. I just look it up quickly or write it down and go off on paper. Yeah. But again, the chart will help you make that ratio, right? Yeah. Okay. Let's see. Let me see what else we have left, and then okay, we're good on time. So let's try just a simple question and see. You know, this isn't doesn't have an exact answer. Notice the numbers are just estimates. Let's say you have the distance between 2 cities and it's marked as 100 miles. The distance between 2 cities is 100 miles. What is the number of kilometers between the 2 cities? So you might say, well, what's the
Less.
kilometers per mile? Okay. We have less, we have more, we have larger. I see lots of different answers. I'm gonna put this out here. That's okay. And most of these quick quizzes, when you answer them quickly, almost always you'll sit there and then think about it and then be like, oh, wait a minute, that wasn't my actual answer. Yeah, so think about that too.
So if there's more kilometers in 1 mile, then that means there's less kilometers. No, wait. Never mind.
It's okay.
If a kilometer is bigger than a mile, then there has to be less of them in 100 of miles. So it's smaller?
Kilometer is smaller than a mile.
No, because let's say like for every $1, let's say like for every $1 you have 100 pennies. So if you have like, because there's more pennies in $1, so if there's more kilometers in 1 mile, then there's more. You know, if that makes sense. I don't know if I said that right.
So here's our conversion, right? Our conversion is 1.6 kilometers in 1 mile. So you can write that ratio. Yeah, 1.6 km. 1 mile. That's okay too. Yeah, that's okay too. So having this ratio helps you, knowing that we're now going 100 miles, right? Here you can do that cancellation and see 100 times 1.6, and our answer should be larger than 100. But it's really easy to get these questions wrong. Yes. Oh, Kian got our exact value. Thank you. It's really, it's really easy to get these questions wrong. Not wrong, but like it's almost like they're not meant to trick you, but they're meant to just make sure that you're following step by step. So take the time to read these. If you just want to answer quickly, the next thing you want to do is prove your answer. If you can prove it, then you're good to go. Once you're in that proof, that's where you'll see that you'll be like, oh, wait a minute, this might be a different answer, and that's okay. That's what you want. It's better to get it wrong and figure it out than to just guess and be right as a guess. Or David says, always guess C. Yeah, that's a strategy. 1 in 3, right? When you'll get there in some way. Okay, was that the answer? Yeah. Okay, here's another a nice conversion problem. On an interstate highway in a rural region of Wyoming, a car is traveling at a speed of 38 meters per second. Is the driver exceeding the speed limit of 75 miles per hour? So we need to take this number and convert this meters to miles and seconds per hour. Henry says, hey, you know what? It sounds like it. So let's, just based on estimation, let's say we think yes, right? Now let's prove it. Let's do the conversion and see if we are in fact right. So we start with 38 meters per second, and you want to start step by step making the conversion to miles per hour. So focus on 1 unit first. Let's focus on the meter. We make the conversion of 1 mile per meter. And here is a good example of how we flip the ratio over based on what we needed. We want the answer in miles, so the mile needs to be on top. And so we just flip the ratio over. This will work any way you write it, as long as the numbers stay with the unit. So 1 stays with the mile and 1600 stays with the meter. Next, we focus on the seconds here. We want the answer to be in hours at the bottom. So we keep our hours at the bottom, and we go from 60 seconds per minute and 60 minutes per hour. And then you have 85 miles per hour, right? And so our question then is the driver exceeding the speed limit? So this is not your answer, although this is the proof to it. You want to just make sure that you're answering the question. And so the answer is yes, he is speeding, and Henry's estimate was right. And Jose says you could get down a step by doing 3,600 seconds. Yeah, that's assuming that you've already memorized that 3,600 seconds. And if you have, go for it and do it. And if you haven't quite yet, that's okay too. So this is a good example. And let me just put out there, guys, this is the type of question I would ask on an exam. And this would be a question I expect you to answer in less than 5 minutes. It's straightforward. It's a matter of just getting the conversions right. There's no tricks to these questions. It's just straightforward convert. You know, I think you'll see that the homework problems are harder than these, but you know, good practice. Okay, so let us do our last thing on this chapter, and then we'll finish. The last thing then, yeah, someone says, I love those types of problems. Me too. I just want to see that you can do it. That's it. No type of Nobel Prize winning trickery involved. Okay, we have some answers already. So the next thing and the last thing that we need to, you know, complete our physics language is significant figures. And so here, there are a lot of math rules, but we want to really think about it. What is important? Are the numbers significant? Are they telling us something, or are they just telling us an estimate? You know, which one is it? So in this number, 1,500 grams, we might ask ourselves, how many significant figures are there? And we have 2 answers. 2 people say 2. Someone says indeterminate. You know, the limit does not exist. That
trailing zeros are not significant if they do not have a decimal point after them.
That's a great way to put it. Yeah, and Amir's adding that too. And several people say 2, some people say 4. Noah's being bold and saying, you know what, I don't conform to this type of number rules, and he says 0. Really, I gotta tell y'all that the answer here is this is ambiguous. These zeros are ambiguous. Now, this is the general question would be, which way do you go? And here, someone could someone could argue 2 and someone could argue 4, and they could both be right. I tend to agree more with what Randy said and what with Amir wrote about the decimal, and and Owen also about the decimal points. And so if this were me, I would say that it were 2, because these zeros to me look like an estimate without there being that actual decimal point. And so that's our rule in this class. The zeros may or may not be significant, and it really matters what the zero is doing. Is the zero a placeholder to get to the number, or is the zero an actual number beyond the decimal that is telling us about exactness of number? So
there was a like in my physics book, like for physics 11, there was a bar they put over the zero to signify if the zero was significant or not.
Yeah, you know why that is? That bar means that it continues, right? So I could write, I think that's what the bar means.
Well, that's what I thought it meant until I asked the teacher and he told me that.
Yeah, but what that answer of it just,
oh, okay.
Yeah.
Oh, yeah. It's for both.
Yes, it means both. It means that it's continuing, but the fact that it repeats means that it's exact and it's significant, that it's true. And so that will be our rules. So for example, here we have 1.500, where these 2 zeros are past the decimals and are not providing a placeholder. They are telling us that the value is exact beyond this number. So here we would have 4 sig figs. Here we would have 3, 1, 2, 3. We have 3, and here we would just have 2. If I were to write 0.500, this would be equivalent to 4 sig figs, because this first zero here, is just a placeholder to get us to the actual value. And then every zero after that is significant. If I were to just write 0.5, this would only be 1 sig fig. Okay. Okay, there's a typo in this next part of the slide, but I like the typo, so I leave it. You guys tell me if you figure it out. And so here's more examples, right? 2.3 times 10 to the negative 4 is 2 sig figs, and you can also write it in standard notation as 2 sig figs. And
that's 10 to the negative 3.
That's the typo. I love that typo. So this is actually 0.000, right? 40023. So this number is actually wrong. That's the typo in the slide. Once in a while, I leave the typos that I find. And there are always typos. So you guys don't just take what I say as truth. Yeah, but if we find them, point them out. Okay, so this would still be 2 sig figs, even though we wrote out so many more digits, right? And the same with this one, 2.30 times 10 to the negative 4 is 3 sig figs. So our 3 sig figs would be written out 230, because this 0 tells us that there's some exactness, versus writing like 231. These are 2 different numbers. So that's our sig figs. So our rule in this class, and just like in the math you've learned before, is that whatever the lowest sig fig is in the problem is the sig fig that you will use. When in doubt, go with 3 sig figs. When in doubt, go with 3 sig figs. I'll usually remind you of this, at least on the first exam, I'll remind you of this in the questions. Yeah. Neil has a good one. Let's answer this one, everyone as a whole. What about this number, 1500.30? Okay, I see lots of
or 6.
Yeah, a lot of you are saying Henry, Owen, Luis, Alexandra, and I think that was Randy also saying 6, and I would agree with 6, because this is exactness. It's not a placeholder. Yeah. And Nate and Mehmet also agree. Yeah, I think this is 6 for sure. Yeah. So what about this one, guys? Let's try this one. What about that number? I wrote out 150.00. Oh, we have
still 6.
I see a mix of 4s and 6s to me, and I think it's still 6, because the exactness of the decimal carries us over. Yes, because of exactness. That's right, Luis. Yes, Amir, it's 6. So that decimal really tells us a lot. So if we were to write 1500 with an awkward decimal there, this would be 4, because that decimal tells us it's exact. This one would be 6, but we go back to the example up top where there's no decimal here, and we say this is only 2. I would argue that this is 2 because I don't know if this is exact or not. Yeah. How do we feel about? Uh-huh.
I'm not sure if this is something maybe you'll get to in a second, but in the book there was this thing that it explained about rounding, and if it like ends in a 5, if it's equal to 5, and if it's you round to the next even number, but that didn't make sense to me because both are it says the closest even, and like so if it's say 0.35 and you're gonna round the 3 to a 2 or a 4, it's good. Both are just as close. 4 and 2 are just as close. It doesn't say up or down. It just says to the closest if it's equal to 5.
Oh, it means in the direction that we're moving. So just like you would read a book from left to right, you wouldn't go backwards. So you would go forward. But you bring up a really good point about rounding up, and I actually don't have anything else after this slide. So let me make this point because people will do this on the exam all the time, and it happens often.
It was a little contrary to the rules I learned prior, the even or odd, the equal to 5. I just was 5 is up and 4 is down,
Yeah, that's what I've always heard too. But 4 is down because we're not assuming higher, we're assuming less. And less would go down. It's which one it's closest to. And so the 5 would always round up because that's our
It says that if it's an odd number or something, then it rounds to the nearest even. If it's equal to 5, that follows that rule. But if it's equal to 6, then if it's 6 or greater, or 5 or greater than 5, then it goes up. If it's equal to 5 in the number before it's odd, it rounds to the next even integer.
If it's 5 or above, always go up, no matter what it is.
Okay, so that rule is null. Okay.
Yes, thanks, Randy. Let's null that rule out. Mostly, one, I don't think you'll ever get into this conversation unless it's like a mathematician who specialized on rounding. Yeah, 5 and up, always round up. 4 and below, always round back down. Rounding only, listen carefully, everyone. Rounding happens at the end. Rounding happens at the end. Sig figs happen at the end. So even though, let's say you have, dang, I wish I had a blank slide. Give me let me see, do I have a blank slide anywhere? Hidden slide somewhere. Okay.
Professor, can I ask a question before you change the significant figures slide?
Yeah, go ahead.
So on the last part with the it had 0.000230. Sorry, it's a little loud over here. I'm still trying to understand why it's 3 sig figs and not 6, since there's a decimal in the middle.
Yeah. That's a good question. The decimal here and these zeros do not tell us anything about the value of the number. These zeros serve to get us to the actual number. So these zeros are placeholders. Each of these zeros will there's no number there. So it only serves to get us to the actual number. So when the 0 is a placeholder to get us to the smallness of the number, the 0 is not significant. And the word significant, it really gives us a clue, right? Significant means, is this number important? And the number is not important if it doesn't tell us anything. The value 2 versus the value 8 tells us that it's either close to 10 or close to 1. Whereas the value 0 in that number doesn't tell us anything about the measurement. It only tells us that we're not close to the actual physical measurement yet, and we have to get there. And that's what these placeholders are.
Okay, so even if there was 2 zeros before the 230 or 1 0, those would also be placeholders, right?
That's right. So if we were to write 0.023, this would only have 2 sig figs right here. These two do not count. If we were to write,
Okay.
let me
Point
just,
zero 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 one. There's just one.
that's correct. If we, and let me write that one out because that's a great example. I can write all these zeros, but the number that matters is this 2. And so all of these are placeholders and we would only have 1 sig fig here. And this is actually pretty important. So I'm, Esmeralda, I'm glad you asked that question because
Thank you, Professor.
yeah, you're gonna see this. You're gonna see this type of problem. And so let me finish what I was saying about the exam questions. When, or even on a homework problem, let's say the homework problem, I found a blank slide. Also, if you ever wanted to watch the Power of 10 video, this is it's that old one from like the 70s. It's great though. It really helps put into perspective why we need the powers of 10. Anyways, but this is also a nice blank slide that I have. So let's say you're given a problem and that problem gives you the number 0.23. It gives you the number 567,000 or 5,670. It also gives you the number 101 and it gives you the number, I don't know, 55.4. Now, you can go through the entire calculation. While you are calculating, write all of the numbers exactly as you see them. Do not round up. Do not consider significant figures. Let's say now you've done the full calculation and your number in the calculation comes out to be 561.356. This is what your calculator spits out. Now is the time to determine how many sig figs do I need, and now is the time to determine how do you round up. So you guys tell me, if you have a homework problem that involves these 4 numbers, and your homework should always be written in the least amount of sig figs seen, what is the least amount of sig figs seen here?
2.
Yeah, so here we have 2.
560.
Here we have 3. Yeah, here we have 3. And here we have 2. So the number, this solution should be written in 2 sig figs. And now, considering that we need 2 sig figs is when we look at rounding up. So you could write this number somehow in 2 sig figs. There's 2 ways to do this. You could write 560, and this is 2 sig figs. Notice that I rounded down. That is where the rounding happens when you're providing the solutions. So you could write 560 and that solution is correct. Or I think Daniel gives it to us really nicely in scientific notation that also lets us write the exact same number in a, it kind of looks nicer too. Or you could write 5.6 times 10 to the 2. These are equivalent and they each have 2 sig figs. And notice that for each of these, the sig fig portion comes at the end and the rounding up or down also comes at the end. If this number were 568.356 and I needed 2 sig figs, I would write either 570 or 5.7 times 10 to the 2. Does that make sense? The sig figs and rounding happens at the end.
Yes.
Okay, thank you.
Is there a preference as far as like scientific notation? If it doesn't say put it in scientific notation, is 560 appropriate?
560 is appropriate and it'll always be marked right. But my little heart would love to see 5.6 times 10 to the 2 because
okay.
Yeah, I think quickly that way. And what I think, I hope one day you guys agree with this too. Looking at this and looking at this, quickly I can say this one is 2 sig figs because I just see 2 numbers,
Yeah.
Where here I see 3 and I have to kind of think, is that 0 significant or not? But if you write 560 because at this stage of Physics 101, that's what you're comfortable with, that is good. That is correct. You will totally be okay. If you write 561, I'm going to put -1 sig fig, but the problem will probably be worth 15 points. So don't worry.
Wait, repeat that whole thing, that thing you just said about the point loss.
Yeah, so if the sig fig is wrong, I usually, in the beginning, I take off more points,
Okay.
but at the end, I'll just, it'll be minus ones all over the place for things that are minor but important. So if a problem's worth like 15 or 20 points, which is usually what the problems are worth, and the whole problem, the number is correct, but your sig figs are wrong, it'll probably be minus one, a minus two, or a minus three. Because you need to have the sig figs right. Yeah.
And so if the problem won't say put it in sig figs, that's just the expected from now on.
Exam one, it'll say make sure your sig figs are right, but it's expected from now on. Yes.
Okay, understood.
From now. Yeah, and then a question for me. So do you always want two sig figs? The problem determines the sig figs, not me, Dr. Clay, but the problem determines it. So for example, the numbers I showed you up here, you would read the numbers in the problem and determine how many sig figs you need. There was one.
Oh, there's a stipulation I would like clarification on if you can. They specified addition and subtraction differently than they specified a multiplication and division. Multiplication and division, they said the least of the factors, the least significant, whichever one had the least amount of significant figures is the one your answer should be in. And then the addition and subtraction said something similar, but it said like, if you're adding, it's about decimal places, not significant figures. It said put it into the, go ahead.
I think that's right, but my general rule is just the least significance. That's what I'll go with. Just yeah, I again, I think that would be something you would see someone where that rule really matters. But general rule is the least significant figures that you see, even for any calculation you're carrying.
What?
Yeah. Yeah, those are very specific. Clarification. First places is the same thing as the least sig figs. Yes, I think so. And then another one, the least significant that shows up in the word problem, right? Not when you are solving. Correct. The least significant that shows up in the word problem. So.
And so does that, what she just asked, is that about the conversions, or are you asking about the conversions? Is she asking about like conversion factors?
Mm-hmm. Conversions happens here, right? Conversions all happen when you're calculating. You guys look at the word problem and maybe make a note to yourself on the side. The least amount of sig figs is 2 sig figs here, right?
So just what we're given.
Yes. And then after you've determined how many sig figs, do not do any rounding or any sig figs while you're actually calculating, converting, none of that. Just move forward with the problem. And at the end of the problem, you come back to your 2 sig figs and you write it in 2 sig figs, because you could get a calculation error if you round up or if you go to 2 sig figs. Like if you change this to 5.7 times 10 to the 3, this number here, you're going to get a different number in the calculation because you've changed the sig figs for it too early.
Okay. And then like as far as the like conversion factors, is there should we keep the conversion factor to the same number of to the greatest number of significant figures as what we're given? Like, sometimes people will take out, things that are very long in decimal places, because like, are these all exact?
Well, this one is exact and this one is accepted. All these values are accepted. So
these are our standard for our class.
Yes, these are standards, and this is what you want to keep. But just to answer your question, let's say you're out in the wild and you need to Google a conversion, and Google gives you like 10 decimals. I would say 3 sig figs is about right. But if you want to be extra certain, you could go 4 sig figs if you're doing a quick Google and they give you a conversion. But there's no exact rule to that. It's just common practice. What is it that you're going to use to calculate?
And now what if the problem itself gives us a conversion factor? Does that conversion factor then count as significant figures?
No.
Like, do we? No.
No.
Okay.
No. Okay, so this is a great place to end. So our slideshow is over, and I'm only okay. I'm pretty behind, but that's okay. I'd like us, before we take the break, I'd like us to go to Canvas and take a quick tour of Canvas. Let me just change my screens here. I'd like us to just take a quick tour of Canvas and show you a little bit about the homework in the lab. And then we'll take a break because we need a break and I have to use the bathroom. So let me pull up the Canvas window. And again, if you don't have access to Canvas yet because you were added today, this is your moment to screenshot, your moment to write down. If you still, if, and
Sorry.
oh, it's okay. And you also have the recording available. But if you, for whatever reason, still miss something, email me or stay after class and say, hey, can you put that back up? I didn't get it. Okay. Randy, did you have a question?
That was just a hiccup.
Oh, okay. Well, since we're speaking about that, I gotta tell y'all this, that sometimes I have these vision issues and it'll take me a second to get back, and you'll see me doing this a lot. And yeah, I have like bad cases of vertigo. So once in a while, if I ever just need to take a break, it got really bad over winter break. This wasn't the case in the past, but if you see me doing that or just see me pause for a little bit, I'm not frozen. Just kind of give me a second to get myself together. Especially coming back to class now with the two screens, I'm trying to move my head slowly. This happens when you get older, guys. So take care of your health while you still can. Okay.
I went to see an eye doctor the other day, and they told me that like us being on computers all day is caused like a myopia epidemic, where more people than ever now are nearsighted and they need prescription to see far away. And
Yeah.
that is if you keep continuing to do it, your vision will continue to get worse, and there's
Yeah.
nothing we can do.
Yeah, I'm already nearsighted. I wear glasses. I have my contacts in right now. I actually will see the eye doctors this week, and I was gonna ask them because, yeah, I don't look that old. Thanks, Daniel. Add like 5 to 8 years to whatever age you think I am. Yeah, I'm gonna go see the eye doctor people and ask them more about my vertigo issues because it's getting worse, and I don't want to have something happen in class. So yeah, if you see me moving slowly, just kind of give me a second, and yeah, any patience is appreciated. Oh yeah, Keon, the blue light blocking glasses. Everyone talks
Oh
about
yeah,
them.
I
Hmm.
got them in my prescription.
Do they really
But they
help?
said that well, like the people that sell you the glasses tell you that they help, but the doctor herself said no, nothing you do will help other than focusing at 30 feet away for most of your day. But
Yeah,
you can't do that with a computer, you know.
yeah, I agree with what everyone's saying. Wow, look, everyone's awake. Okay, well, I'll do a lesson on these blue light glasses because I also go back and forth, and then my general kind of understanding is that perhaps in the long term you'll see a little bit like better or not better, but your eyes will feel better. I don't know. Um, but what I've learned is that I need to cool it on the caffeine when it comes to my vision, and that I need to not move my head so quickly and step away from the monitor.
They say caffeine affects vision?
I
It
didn't know that.
affects it affects like the way your there's a tie to vertigo with the balance thing that you have in your ear and having too much caffeine. Just I'll be very honest with you guys, and this might be too much talking, but hey, we're awake and we're in class. um like you guys, I once in a while I really struggle with motivation, and class and work really helps me structure my day. And so during the winter break when I had no class, I struggled with like being productive the entire time. And so the thing that gets me going is coffee, but I was having like 3 cups of coffee before like 10 a.m. And it wasn't until like the fourth or fifth day of doing that I started having these major vision problems. And so since then, I kind of, I've stopped it again, but it's helping. So everything in moderation, guys, even while we're trying to get through pandemic stuff. So yeah, come to class, wake yourself up. Yeah, and I agree with Bradley. I night mode everything I have. All my screens are night mode. You actually see it right now. Yeah,
It
and
helps.
yeah, and I agree with Keon. Green tea is my new coffee too, right? We put yeah, and I have I'm with you guys. Yes, Jose, eye drops have been working too. Ah, matcha tea. Okay. I'd love to hear anything from you guys that'll help my vision too. Yes, the matcha. Um, okay, so I'll take us back to Canvas, but feel free to write in everything you want to add. Anything that helps with motivation, I'm here for it. Even talking a little bit too. Yes, Owen, I'm on the water thing too. Um, okay, so you see our Canvas page here, and I hope since yesterday you've had a chance to explore. And again, if you're just adding, I promise that you haven't missed much. I only published the page on Sunday, and I put the wrong syllabus up, so you haven't missed too much since yesterday. So before I get to the assignments, let me just give you a overall look, a global view of what our Canvas will look like. This is what your Canvas page will look like the entire session. This first module and these blocks here are called modules. This is our homepage, and you'll have our welcome module where you're going to find all the general information. And then you'll find the 5 buckets or categories of this class, which just happen to very nicely align with the 5 weeks of this class. And each module will sum up a topic. Each topic will have a few chapters. Each topic will conclude in an exam. So everything you need for this week and this module and this section will be under the first module, which is Fundamentals of Kinematics. Now, what you'll see every week is a page of that chapter, and all the chapters will be available at the beginning of the week. So this week and this exam will cover chapters 1, chapter 2, and chapter 3. As we go through the chapters, I will publish the homework that goes with it, and if there's an associated lab with it. I mentioned before that I'm going to try to have 2 labs per week, generally on Tuesdays and Wednesdays. So however that works itself out, it'll be about 2, and so you'll see them here. So if you click on the first page, physics and measurement.
You said, sorry, I don't mean to interrupt, but you said 2 labs per week and 2 activities per week?
No, I said two labs per week. That's correct. And you'll have a homework, which is an activity per chapter usually. Yeah.
Okay, so each day.
Every chapter.
Oh, okay.
So, yeah, and because one week we'll have 2 chapters, so there'll be 2 homeworks, even though it's 4 days. So per chapter. Now, when you click on this page, you will see the slides here, and the slides will be nearly identical to what I show you in class. In the past, I took all the solutions out because the solutions are available in the textbook. They're also available in class, and they're with you in the recording, so you can take the time to write them out. But I think once this pandemic hit, I was like over it, and I think I included some solutions. So I don't know if you'll see it in the future chapters, but the slides are there. I'll always put the recordings here too, but this is not what you should depend on to watch the recordings. The recordings are available on the Zoom link right here, and that's the quickest access you'll have. This depends on, how quickly I get the link in the email and how quickly I can remember. Additionally, every chapter will have a corresponding crash course video. I love these crash course videos. I think the crash course videos are fantastic, but, and here's why they're fantastic, because they match our textbook and they match our timeline of how we will go through the topics. The crash course videos are about 10 minutes. You should watch them after lecture, and you should probably watch them after you've read a little bit too. Thank you, Keon, for the link to the solutions. Everyone, the chat will close at the end of the meeting. Click on the link that Keon put out there. We appreciate it.
As far as Slater being free, so Slater, I've never had this happen to me before, but I guess I'm using a college level book now, and all my other books were not. They were considered high school, even calculus, and so I get very limited number of solutions. So I actually had to yesterday I had to pay for it, Slater, because you can see the little previews and you can go online on the computer and see it, but on the app, like to open those previews up, you can only get like 6 of them or something.
Yeah.
And then it asks 6 per day.
I think they changed that recently because it used to be free
Yeah.
for all my books, but I think in the last like maybe year or so, I think they updated it and they made it so that you have to pay.
Like my other books still let me view them all, but this book, because it said that it was a college level book, that I had to pay the college plus fee. But then they also provide you with like one sheeters and stuff with that membership, like extra stuff, which I'm happy to do, and they take away the ads, which the ads killed me. I used to buy stuff when I was doing my homework because they'd pop up with relevant things.
That's what's happening to us all right now. But whatever resource works for you guys, please, feel free to use it if you're able to buy the membership and it makes sense to you, then go ahead and do it. I always think anything that you pay for your education is very much an investment. And if you guys are paying $8 a month or whatever it is, $10 a month, you're probably paying more to go out to eat or to, I don't know, buy something quickly on Amazon. So we talked about this yesterday. I'm not against you guys using any solutions. I'm very thankful that you're sharing this with each other. Use it as a guide. It is a good guide when I'm not available. Use it whenever you need. Oh, and Henry gives us some tips. Thank you.
Yeah. I didn't think about that.
We're all like, oh.
Does anybody know how much Chegg is? Because I already bought the thing for 4 months, but I guess I'll do Chegg later. Does anybody know how much it is?
I don't. Okay, we have like 13, 15-ish. So consider it, guys.
A month.
Anything that'll help you guys out, I'm all for it. But do know that after the homework is turned in, I will always post solutions to the homework. But if you need it to help you with the homework on Friday evening and I'm not available through, because I'm not checking my email for some reason, find whatever you need to help you. Just submit an assignment. And again, the homework assignments, I grade them on completeness. So complete it. Okay, so let me get you guys back on this page. So I recommend, again, the crash course videos. The only thing is that the crash course lady speaks incredibly fast. So they're 10-minute videos, but you do not want to, you do not want to, text or be watching something else at the same time as this video. You really want to focus on it because they go fast, but they're really good. So, okay, so that's our first page. Let me take you back. And now let me show you, again, you'll see this you'll see our slide set and you'll see the video. Eventually, you'll see the recordings updated. And Destiny, yes, some people have started links. I think there was a Discord link yesterday, so y'all help each other out and put that in there. Okay, before we move on, okay.
The link I got yesterday doesn't work for the Discord, so if anybody could put that in there.
Yeah, you guys put that in there. So let me take us to the first homework. Okay, we got a new link. Thank you, Henry. The first homework is available here, and usually all the details will be on here. So the first thing to note, and I see a question about the homework and I'll get to it also. The first thing to note is to read the entire assignment and the details. It is due Friday at 11:59. Everything in my class is worth 10 points, but it's literally just a matter of laziness instead of writing 100. So you can think of it, if you get a 9.1, it's like 91. It's literally me just.
Hello?
You're frozen. Yeah, DDoS.
Hi.
Maybe your internet went out. Loki.
I don't know. She's good on my end.
Cutting off a 0. That's a
It's froze. Oh, she just came back.
Yeah, she's like kind of coming back.
Am I back? Am I back?
Yeah,
You're back.
Okay. if this ever happens and I get kicked out, I really thought I was gonna get kicked out right now because I saw everyone freeze too. I will be back. Don't go anywhere. I will be back. Okay, so I think perhaps I heard someone tell me I got frozen around this top line right here. So this top line will tell us this top line will tell us everything about logistics. Everything must be in a PDF. So just get comfortable with PDF. We had several tips yesterday from you guys of the PDF. So yeah, PDF. I'd really appreciate if you guys could figure out how to combine your documents so that you can submit everything as a single PDF. A lot of the apps that you're using let you do that. So I don't want a page per problem. I don't want a file per problem. One single PDF. If it's a page per problem, I will probably skip grading your assignment and come back to it at the end. Just because it messes with the flow, and it really will take more time to grade versus grading like 10 assignments. So please do your best to submit everything the way it is on here, and you'll see, you submit here. Okay, the homework problems are listed here. Notice that there are only, what is it, 6 of them. There's usually 5 to 6 problems, and you would just submit the solutions to them. In this homework problem, there's a review sheet, and this isn't always the case. You'll see this again in the first week of Physics 102. This is just, to give us some practice on angles, which we're going to use a lot on Wednesday and Thursday. And also to help us practice the unit conversions that you see here, and that we talked about today. And so the first one tells you, I hope it's large enough, convert each of the following measurements into specific units. And I had someone ask me, how do you want these answers? Do you want them in scientific notation or in standard notation? The real answer is in this case, it should be standard notation, which means the number written out. But if you feel comfortable enough to put it in scientific notation and it's correct, then I'm okay with that. I think the answer is right. So I'll still grade it as right, but standard notation is the way to go here. And then finally rank these measurements from smallest to largest. And again, the way to do this is to go to the base unit first. So take everything to the single gram, and then, you can compare them all to each other. Okay, so that's our first homework, and I had a question. Let me scroll back up. The first problem of the homework says to look at the end papers. Where is that located? I think it's the appendix in the back. Anyone know?
So I didn't find it there, but I did find it in the chapter. I looked at the beginning and I couldn't find it. But it might have been I didn't look at the end.
No, well, if the end papers probably is the end of the chapter. That sounds right too. So look in the end of the chapter, which is graphics. Yeah, I don't know what end papers means. I would just assume the back of the book.
Oh, that was the end of the book.
Ah, okay.
That's the end of the PDF.
Ah, okay. Thanks, guys. That's where you want to be. Oh, on the
So
PDF.
it's at the end of it, not at the beginning. I looked at the beginning because that's where I thought the most conversions and stuff in books are at the beginning.
Yeah. So
yeah, it's the last 4.
The last 4 pages. Thank you.
But it's also located in the chapter too.
Thank you.
In the reading in the tables.
That's what I want to hear. I want to hear resourcefulness of just looking for it too. So good to ask and good to figure out. And I also see lots of tips in the chat about the PDF and where to look. Okay, so let me take you guys to the lab that's due on Friday. So again, the lab and homeworks will always be due on Friday by midnight, always a PDF. This first lab is very much an exploratory lab, which means that you can do pretty much anything you want as long as you have, the parameters here, as long as you follow these and include this. So this is an at-home lab. You will identify any 5 objects or a situation around you using, and you will identify the units. So you will use each of the fundamental quantities and identify those objects using the units. So for example, Keon earlier showed us his old school computer that had something, was it like kilobyte?
2 kilobytes. 2 kilobytes. Yeah. Oh. It's like 1 page of text.
So let's use that as an example. So this is an object that Keon has pulled up. And in this object, he will describe what he sees using the appropriate units that are known because you looked at the label or a manual, or because they're assumed by everyday use. For example, you look at a clock, you know, it has 12 hours in one circle, you know, you can go that way. For some of these items, it might be helpful to look at the tags, the labels, the manuals, or the instructions. So for each of these objects, this is what you will include. So for the computer that he has, a drawing or a photo with clear labels. The drawing or the photo can be a hand-drawn image, or a picture that you take and then put in the file, and then you label telling me, you know, what it is that you're taking the unit of the computer, label with what it is. And then a brief description using the units in the description. So I think Keon just gave us a one-liner as to what the computer was, and that would be a perfect description. It's a computer with basically one line of text that provides one line of text and uses something kilobytes.
2 kilobytes.
Yeah, 2 kilobytes. So that's a perfect description. Now, within that, you see that the fundamental quantity that's described. Oh, which one is it?
So it's none of those, right?
That's correct. It's mixed.
So it has to be one of those, right? It has to be a fundamental quantity?
Yes, it does. But the kilobyte is actually a motion of particles moving. Now, do I expect you to know that? No. So if you know it, cool. You know, no problem. But here, you don't really know that. So Keon, if you know it, you go ahead and, you know, if you really want to know it, look on Google and type in SI unit next to it. And yeah, it'll pop up. But if not, you know, yeah, that's the way to do it. It'll take you through a long wormhole of units. So make sure you mention what is the fundamental quantity measured, and then what is the SI unit. Sometimes you might need to convert. We're in America. Randy?
So I have like a kind of a, it's a question, it's about this, but it's kind of specific. So if I have kilometers and I have milligrams and I have milligrams, is it okay that I have milligrams twice? They're two different amounts, two different labels?
It's okay as long as the other objects will use, you have to use length, mass, and time at least once.
Yeah, I use length once, mass once, and time once. But some of them got EWs.
Yeah, that's okay. So finally, you're going to submit this as a PDF. And of course, you can submit anything late that you'd like. So this is really exploratory, 5 objects. Draw them out, write a description that tells me what it is, tells me about the unit that it uses, you know, when you describe it in everyday language, and what is the SI unit that you're using there. Any questions about this lab?
Yeah, so we're not like measuring anything ourselves. It's just whatever isn't like on the label.
Correct. That's correct. Now, some of these can be assumed by everyday use, and that's when I say like anything that you want to just assume that you know a value for it, because I don't know, let's say the microwave heating, a situation is like heating up a cup of water, right? That will take you 1 minute, let's say. And so that you could just make up. But most things you're not measuring yourself. Henry says, can we measure the objects ourselves? Absolutely. Absolutely, you can. You can do anything you want as long as you do this for 5 objects or situations. Anything you want, even if you want to Google it, I don't care. As long as you write this and understand what you're writing, it's all good. Yeah. And as long as I get a PDF in the end, it doesn't matter how you make that PDF. Okay, I hope that answers your questions, but if you have more, we can come back to it at the end of class. And so you'll see the homework here and another lab here eventually. We will get to it. We will have time for it. Don't you worry. The last thing I want to show you is the welcome module. Here's where you'll find our syllabus. You know, we should double check that it's the right one. It says 2021. All right, it's the right syllabus. So go through that in detail. You'll also find a quick link for our Zoom class. It's also up here, but if you want to just, you know, this is already open, go there. I uploaded this flyer yesterday. I got it from one of my past students. Academic Connections is open and ready and available to help for tutoring. I love everything about Academic Connections, especially the tutors, because they're all my past students. Every single person that tutors physics in there and probably math in there too are all students from my class. So they can very much help you with anything in this class and physics, and they've seen the material. So this flyer will help you get in contact with them. If you have any issues whatsoever with getting in contact with them and you're not getting an answer of any sort, you can let me know and I can try and help or figure it out too. Yeah. So we'll also have a visit from one of our physics tutors tomorrow morning at 10 a.m. So make sure you're here. And then the last link is a page that I made that just gives you all a quick stop of links that'll help you at trade. So anything you need, meeting with our counselor is really good. Anything that you need specific to applied sciences, tutoring will take you to Academic Connections, things like that. And then finally, some specific services that might help you, and I very much encourage you to look at them. Some of the services I think you should look at right away. Probably the best ones are DSPS, and this is all student initiated. So if you at all feel like that you need more support in your learning in this class or any class, talk to one of the counselors at DSPS. They probably have some sort of solution for you. Also, EOPS gives you so many great resources on campus, including very specific counseling support, money for books. So go there too. If you're a veteran, go to the Veterans Center too. They have a lot of good resources. LA College Promise, Puente and Umoja will also give you a lot of academic support. The Dream Resource Center is fantastic resource for anyone that's undocumented, DACA. I also know a lot there and can help you with anything that you need there too. So take a look at our canvas. Any questions for me? Okay, I think we all need a break. Let me stop sharing and go really quickly to our chat. Okay. Thank you, Patricia. I'm glad you're actually looking at the info. And guys, at any time, our Canvas page is a one-stop shop for any help that you need. I think we're going to take a 14-minute break. We're going to go a little bit more than the 10 minutes today. We'll come back and we'll do a half hour of chapter 2, and we'll just see how far we can get with that. Again, everything we will adjust, so don't worry at all, and we'll get through it. Yeah. Are we okay with the break? 12 o'clock? Okay. Yes, I'm with you guys. Okay, thank you. I see all the thumbs up. Thank you, Sanjita, Ayla, Saja. I appreciate it. All of you in the chat too. Yes, please. I'll see you guys at 12 o'clock on the dot. Get up, get some water, move your legs. I'll see you all very soon. Hello, we're back. I see you guys. Hi. Hello, Brian. Hello, Mehmet. I see you all. Hi, Patricia and Brian. Okay, guys, I hope you got a minute to stretch and you were good. Hi, Neil. Hello, everyone else. Robin and Jose, good to see you too. Owen, you're back. I'm glad. Um, Okay, so what we want to do is get to chapter 2 and see how far we go. And yes, we are back. So I'm going to share my screen and take us into chapter 2. And this is where physics starts. So this is probably the time to start writing some notes here and there, or just make sure you're following along and go back and read later, and you could always fill in notes after class too. That's probably the best time to do it, is after class. Okay, let me start my slideshow and let me move my screens around while not moving my head so quickly. Let's see. Okay, and let me just get my chat box open. Perfect. Everything's exactly where I left it from the last time I shared my screen. Okay, so everything we did in chapter 1 was about, creating our language for physics. How are we going to describe things? Making sure we're all in the same, starting off at the same point. Now in chapter 2 and then the rest of Physics 101, our entire lecture will be about motion and how we can describe something physically. And little by little, we're just going to add to it. You'll see that when we describe anything in motion in our world, we usually talk about something being fast or slow. And when something is fast, there's numbers and units behind that. And that's what our job is going to be, to become exact with how we describe everything. So we are going to start by describing how motion happens in one dimension, so along a straight line. And that straight line will usually be the horizontal line that we see, like along the x-axis, right? But you'll see that eventually everything we do on the x can translate to the y. Everything from horizontal will eventually translate to vertical in the same way. So the reason we study motion is because it's one of the things that we can physically see with our eyes, large objects that are moving in space. And given anything that we have around us, using reference markers from anything we see out in the world, you could say something about motion, whether it's fast, short, long, slow, how long does it take? So motion is something that all of the early scientists studied. And in fact, from all over the world, we see that the one thing that is common in the study of physics and motion, from Europe to Asia to North and Central South America, are objects in the night sky, because these are things that are common to all of us, going back to how we establish our measurements for units, right? And so we started seeing more specific studies of motion when scientists like Galileo or Isaac Newton were looking at how one specific object would move and tying that relationship to larger objects that we see around us. So for example, Galileo was studying how objects fell off of the Leaning Tower of Pisa to make the argument that everything falls and accelerates with the value of gravity. And it's very impractical to go to the top of the tower and drop different items and have someone kind of try to measure how long it takes to do that. And so he modeled it instead with inclined planes and creating larger down to smaller inclined planes where he could reduce the speed of an object and more closely figure out what are the timings between something falling. And then Isaac Newton really looked at how is it that an object is falling down. And this is where the whole story of the apple comes in, right? What does it mean that something falls down? In a few chapters, we'll clarify that down is really to the center, not necessarily down in our direction, but to the center. So the study of all of this motion really brings up a lot of questions of how can we make a pattern for all of this, and that's what we're trying to do. we're going to try to come up with equations and math to support what it is we're trying to describe. And yes, things falling down due to a gravitational pull of some sort. That is what Isaac Newton was studying, and also Galileo. And it's really nice that we have both of these names up here, because the math needed to describe precisely how objects are moving was invented by Isaac Newton, because we didn't want to be in the world of averages. We wanted to be in the world of exactness, instantaneous motion. How can we very precisely describe something? So let's say you're out on the road and there's nothing around you. Well, as a scientist, you could at least establish that you're driving down a straight road, and that's a straight line. You could look at anything that you see around you, like these poles, and notice that the poles, the electrical poles, are spaced out evenly. Because they're spaced out evenly, you can start to say something about how fast you move past a certain number of poles. And that in and of itself is starting to describe the motion of your car, how fast or how slow you're going. Depending how many poles you pass, if you pass 10 poles in 2 seconds versus 20 poles in 2 seconds, you could say you're moving faster. And so this is what we're going to study. From our everyday experience, we're going to look at the motion of an object and look at the motion of an object as it changing its position. Changing a position over time. This is the foundation of everything in physics, and everything from physics 102 to 103 will eventually dwindle back down to how does something change its position over time and how we can describe that. So just like we did in chapter 1, the first thing we got to do is define our terms, right? I'm just setting up a timer so I know not to talk too much. And so we'll start with, how do we look at position, defining position, and then what is the change of that? So here's our definition for position. We are going to work mostly on for this chapter in one line, and horizontal, which in math, you know that to be the x-axis. So we'll use the letter X to denote position. And this will be the location of a particle with respect to a chosen reference point. And I want to emphasize this, that this reference point is chosen. We decide where the 0 goes. We decide anywhere in the problem where the starting point is. And we can move that as we please and as is convenient to us to solve the problem. But we do need always a reference point, and that is some sort of origin on your graph. That's that center point, somewhere to start. So you can show the description of a car moving in different ways, and this is one way to show it. First, we start with our reference point of 0, and then we see that there are increments of distance described by this x and the unit of the meter right next to it. And we see that they're equally spaced out 10 meters, and we see a car at different positions. So the car here is moving from point A to point B, and then it moves back to point C, back to point D, to point E, and to point F. We could also show this same exact data that we see with this visual image, right? We could also show it with a table, and now we could get more information out of this. This same information is now on the table, and we can now see that between every measured point is 10 seconds of time. Now we have some kind of equal spacings out here. So position A here, and we'll measure it at the center of the door, it's about 30, is time equals 0 seconds. So we start there, and we're at position 30 meters. And 10 seconds later, we're at position B, which is at 52 meters. And you see, just like the picture shows us, we're gonna move backwards. And so 10 seconds later, we move backwards to the 38 meter position. So the table very nicely kind of shows us what the picture is showing, and we can pull the same information from these two things. Now, as scientists, our goal is to take any representation that will help us, but really we want to eventually get to a mathematical representation. So we can take this data and we can plot it on a table, on a graph, right? And this is what the plot will look like. Notice some things from this graph. First, we have our origin. Then we have our x-axis labeled with the unit, the physical quantity, and the unit that describes it. And we have the unit on the y-axis too. So we have our reference point and we know the language that we're speaking, meters per second. And you take every point A, B, C, D, E, F, and you plot them here. Now, notice that we have the points A, B, C, D, E, F, and in every increment of time, we can go, right, 10 seconds, you know that you've moved this amount of position over. So you know where you're at position A, and you know where you're at position B. But notice that we have this curve that's kind of connecting everything here, right? So when we look at this, you want to be very careful in identifying what it is that the graph is actually showing us. The smooth curve that you see here is really a guess, right, as to what's happening between the points. The smooth curve is an estimation, right? It's telling us what we think the behavior of the points are. Now, at the points A, B, C, D, E, F, 6/16 of those times, we don't actually know what's happening in between those points, but we know at that exact point what is the position and the time that has elapsed. Everything else in between is just kind of a guess. But our goal is that from any one of these three pictures, we can pull out a lot of the physics of the situation and eventually make up some sort of mathematical equation. So we start with position X. Now we want to look at how are things moving from point A to point B to point C. Not really telling us things in between, but just what's happening at those points. And that in physics is defined as the displacement. So here's our displacement, and let's be very, very specific with what is the definition here. The displacement is denoted as delta X. And this delta X defines a change in position for a given time interval. That position, we will define the beginning and the end of what is the change that we're looking at. So this change will be what is the difference between where you end up to where you started. So final minus initial, and this is your equation for displacement. This is, yeah, anything in a blue square you want to write down. Or, you know, if you take your notes later, that's okay too. So the displacement delta X is defined as the final position minus the initial position. Now there's a lot in this equation that we want to make sure we understand. First is this delta symbol. This delta symbol will always mean change. Change will always mean final minus initial, and that's what these subscripts are. You want to make sure you pick up the habit of writing these subscripts, and these subscripts will help you stay organized throughout a problem. You can put anything you want for the subscript. In fact, if you wanted to change this initial to a 0 or a naught, right, X naught, you could do that too, and it'll mean the same thing. The other thing you want to note here is this triple equal sign, and this means defined as. So in addition to it just being an equation, it means that this is actually the definition of it too. It doesn't just show the relationship, but it's literally defined this way. So this is the displacement that tells us about how position is changing, but it doesn't exactly tell us what happens in between. So let's look at the difference of those two. So we can have something called the distance and something called the displacement. So the distance is actually the footsteps, and there's a bug around me, is actually the footsteps that you're walking, the path that you're taking. So a distance of something is the length of the path that's followed by the particle. The particle could be anything. It could be a car, a person, a fly moving around your desktop, and the path it actually took. So it can be, you know, a path this way, or it could be a fly moving this way. That actual, every single point that is drawn is part of the path. So let's look at this. Let's say you have your favorite Dodgers player. We all have different opinions. Let's say it's Kike, let's say it's Bellinger, maybe someone out there's a Muncie fan, you know, whoever you want. And let's say that Dodger player then makes it to second base. Yeah, Neil agrees. Let's say he makes it to second base. Then the distance that this Dodger player goes will be from first base to second place. Oh no, we have some Giants fans in the house. Okay, so let's say this Dodger player makes it to second base, and so the distance or length that that player has followed is, you see here, 90 feet plus 90 feet is 180 feet. And then, you know, perhaps let's say that this distance is then, what is it, 180 feet. Let's say, as is normal, any one of our Dodger players from the roster come up and they hit a home run. They would go from home base to first to second to third and back around. And now, what would we have? 90 times 4. What's that? 360? 36? Yeah? Okay. So then we'd have a home run. 360. Thank you, Jose. We'd have 360 feet. All the way around we go. So this is very much covering the distance. Now, how is this different than displacement? Displacement is the change of the particle, right? Delta x of the particle is the change in position. So let's try this again. Let us say that our favorite Dodger player then goes from the initial position of home plate to the final position of second base. Is the change in position or the displacement the same as the distance?
No.
I hear a no.
Displacement is from home plate, straight line from home plate, and distance is 90 plus 90.
Ah, okay. So we have a length, which is a distance, which is the exact path covered. And this will go 90 plus 90. Wow, you guys make a really good, point here. And then displacement, I'm just going to write delta x as our shortcut, will be the final minus the initial, right? Final minus the initial. So final here is this point right here. So the displacement is actually that distance right there. What is it? 127 feet and 3 inches.
3/8.
Yeah. So that's what our displacement would be. Now let's say this one is coming up to what Neil is asking us. What about if your favorite Dodger player, right, hits a home run, wins the World Series, unlike the Giants, and unlike if we have any Angels fans out there, and we actually win a World Series. Okay, I see my chat blowing up. Hold on, y'all. You know, it's been 30 years. Okay, we win the World Series with these home runs, fair square, no cheating, and now we go from home plate to first base, to second base, to third base, back to home base. What is then our displacement?
0.
Yeah, I see lots of zeros. I hear lots of zeros. I'm not a sore winner. I'm just a winner. So our displacement for a home run here, x final minus x initial, is 0 because final and initial are equal to each other. Uh-oh, we also have some Houston Cheater Astro fans in the house too. Yes. I also got to tell y'all that this runs deep. I went to the 2017 game, the 2018, all of those NLCS. I went to all of them. So, you know, it hurts. But this time it was all good. We won. Yes, mega fan. So you see that there's a very, very clear, yes, I did have many sad years, very frustrating years, losing. Yes, I'll agree with that. But you see here we have a very clear difference between the distance and displacement. And just by looking at this, you can really figure out some quirks about what displacement tells us and what distance tells us. For example, here we have two quantities, each of which can be described by a number, but only one of which can be described by direction. So our distance, for example, is what we call a scalar quantity. It will only have a numerical value and no direction whatsoever. The scalar quantity will only tell us the number. It will not give us a direction because it's not comparing the final from initial. It's adding up everything along its path or for example, from home to here, the shortest path between them. It's taking out the direction. We took out, if we're going from home to second, we took out the whole path along the first. So this distance will only give us a scalar value. And this is a really good example to differentiate that. Now the displacement will give us some direction, and this direction will make it a vector quantity. When we talk about vectors, and this will be at the end of tomorrow and going into Thursday, the vector quantity will give us direction and the number. And look at how specific this vector is. If we get the displacement from home base to first base, we will get 90 feet to first base. If we get the displacement then from home base to second base, you will still get that same, that final minus initial distance, but now you have to specify that you went to second base. There's some direction that's involved there. So let me try to clarify this way one more time. You guys tell me, can a distance be positive and be negative? A distance is an actual...
No, it should just be positive.
Yeah, Luis says no, it should just be positive, and many of you in the chat, Owen, Daniela, and Mehmet also say no. Or Neil makes a really good connection as an absolute value. Jose also says no. The distance is the actual path. Let's say that your feet are moving, and we cannot move a negative distance. We can move a negative direction, where that negative implies the opposite of the direction we were moving in. If we had a positive, then it would imply the opposite. Not necessarily a negative like below zero, but a negative as an opposite of positive, which would mean opposite of west would be east, right? Opposite of north would be south, something like that. Okay, so when you think about distance and displacement, we're almost always going to work with displacement in our class. Yeah, pretty often we'll be working with how things change. So this distance will always be a positive value. Let me get my eraser out here. And the displacement can be positive or negative. But in physics, this positive or negative tells us not where we are with the zero on the left or the right side of it, but it tells us about direction. It'll tell us about if something is increasing or decreasing, not necessarily what a negative would normally mean in like a math class. Okay, so let's try this question. Which of the following choices best describes what can be determined exactly from the table and figure for the entire 50-second interval? So from looking at this table and looking at this graph figure, what can we determine exactly? Can we determine the distance? Can we determine the displacement, both A and B, or neither A nor B?
Both A and B?
Okay, I have several C's. Okay, I have several C's. I hear both A and B, and I see displacement only and B. Where's displacement only and B? Okay, so let's look at both of these. Okay, and I see another C. So this one involves displacement, and option C involves distance and displacement. So let's look at distance. Distance is the exact length that's covered from the exact path that your feet follows, or in this case, the car. At position A, the car is at 30 meters. The car is at 30 meters here. That's a car. I probably should have drawn a box, right? And this is 30 meters. Now, 10 seconds later, the car is going to be at 52 meters. What do you think is the path that's followed from 30 meters to 52 meters? Any ideas?
Right? Or
okay.
Positive?
Okay, something to the right and something positive. Now, Randy,
22?
Is that okay, like 22 to the right and positive? Randy, is that a guess, or is that, you know for a fact that car drove in a straight line?
That's a guess going on the Cartesian system.
Yeah, it's a guess with something that is very common to us. Well, because it's a guess, we don't exactly know if the car went like this straight, which is what we all expect and guess, or if the car went like this. and then
So
landed.
we can only guess
Yeah.
the displacement.
That's correct. So we can only guess the displacement because we don't exactly know. Everything else here is a guess. So when we talk about things that are spaced apart with these large time intervals, let's say 10 seconds or so, you're making averages, you're making guesses, and you're making an assumption as to how something is acting. What is the behavior? In a few slides or so, we are going to minimize that time interval from 10 seconds to 9 seconds to 8 seconds, as close as we can to 0, so that we can get a very exact position at any moment in time. And that'll take us to an instantaneous value and not just an average value. So in this case, just like Randy tells us, is that we can actually only look at what is the displacement. We can only figure out exactly what is the final minus the initial, and we can, with a fact, like facts, say what is the difference between F and A. And literally, that's what we're saying. What is the difference between those 2 points? We're not saying anything about the in between. Right? So Owen says, yeah, calculus time. Yeah, calculus will get us to instantaneous values. Everything about final minus initial will usually be an average until we start to minimize that time interval to something much smaller, right? Okay, I have about 3 minutes left. Yes, this was the answer, the displacement of the car. If you went with C first, that's okay. You just want to prove your answer. After you guess it, you want to justify your answer. Yeah. Okay, so let's come to our first definition then. When we talk about position and velocity of any particle, we can look at how this data gives us, the position of the particle at any point in time. At 10 seconds, it's at point B. At 30 seconds, it's at point D, or at 50 seconds, it's at point F. And so at this point, we can figure out on average, how is the particle acting, but not exactly. And so this is our definition for the average velocity. First, notice that we're working on one line in one dimension. So the first thing that you will see is the subscript X, which tells us that we're only working in one dimension. And notice very specifically, we're writing the average because we usually won't be working in averages. So we're going to specify that we're working in the average. So the average velocity of the particle will be the particle's displacement, delta x, which we know, final minus initial, divided by the time interval, delta t. And notice we see the delta again, so final minus initial. So for this average velocity, let's say between any of these points here, the average velocity is defined as the displacement of x over the time interval which we want, whatever time interval that you want. So again, we have defined as delta x over delta t. And so we know this is final minus x initial. So before we end, let me give you one example, a quick example of this using the chart that you see here. Remember, this delta just means final minus initial. And we're gonna eventually make it easy on ourselves and try to make most of the initials a 0, eventually. So let's say we wanted to look, I'll get to that soon. Let's say we wanted this average here from A to B. Well, what we're doing from A to B is getting that final minus initial, where this is the final and this is the initial. So the final of x is right here, and the initial of x is right here, right? The initial of the distance is right here. So notice this final minus initial covers this line right here. This delta x is the final position of y minus the initial position of y. I know this says x, but it's the y axis. That's what I mean by y. And notice then we divide it by that delta t if we're trying to get the average from A to B. So this is the final time here, right? This is the final time, 10 seconds, minus the initial time, 0 seconds. And this covers this distance, which is also that final position along the x-axis minus the initial position along the x-axis. So something you might notice and probably really want to grasp here is that what we're doing by taking this average is looking at the slope of the line ratio, right? We're looking at the slope of the line. What is it? Rise over run? y over x, right? So always remember this, that this triangle is also the rise over run, which is the same as the change in y over change in x axis, which in our case is exactly equivalent to what we've just done here. Oh, we got some values. Yeah, thank you. Is it two? Yeah. Oh, I think you guys got some good values there. So Vx average, and I'll finish in just a minute, is delta x over delta t. And let me be very clear here that this delta x is not the same as this delta x, even though it seems like it. This is math language, and this is physics language. So you see the difference here too. And so let's just look at the average from A to B. You would see 52 meters right here, minus 30 meters. This is our delta x over delta t. And you get about 2.2 meters. So all of you saying about 2 is right on the money. So this is how we would calculate the average. So what we're going to do tomorrow is look at how we can calculate the average. We'll start tomorrow with calculating the average velocity for a problem, and then right away we're going to go into instantaneous velocity. So tomorrow, put on your calculus hats, because yeah, we'll do a derivative here and there. But all the derivatives you need to know for now are just exponents. So if you can take the derivative of x cubed, you're good to go. And any questions before we leave? I see some already to me, so let me ask that. If this was on the test, are we expected to put 2 or 2.2 for the answer? Which is the next question that came up also from Daniel. Is it 2 because of 1 sig fig? Let's see. So if these were the actual values on the table, according to this, I think we have 1 sig fig. Is that right?
Yeah.
Yeah.
Yeah. I think I would want the value of 2.0 meters per second or 2 meters per second, like you guys all gave me. And that's perfect. Now, let me let me tell you guys that this one is a little confusing, right? Like, why would I, like this, I wouldn't do this to you guys. I would write 52 meters and I would write like 31 meters and I would write like 11 seconds just to be, you know, very exact sig figs, so that you know that it's exactly 1 or 2, and not to throw you off too much like that. But it's very good that you all identified this. So yes, if this were the problem on the exam, this would be 1 sig fig and this would be the correct answer. 2 meters per second. That would be the correct answer. Yeah, that's a really good thing you guys all pointed out. Okay, I'm 3 minutes over time. I'm very sorry, but appreciate that you all stayed. I promise I really don't usually go over. It's just these first few days, I guess. I don't have anything new for you guys. I'm going to publish the homework for chapter 2 in case anyone just wants to get started. But if you don't know if you have a question about it, that's normal because we haven't gone over it. But I will put it out there in case anyone wants to start on it. You won't have a lab associated with this chapter, so just kind of hold tight and make sure you get all the other assignments in. So before I leave you guys, and I actually not leave, but before I hit stop record, any questions about today?
So we should read chapter 2 for tomorrow. And
yeah,
or were we supposed to read chapter 2 before the lecture?
It's always helpful to read maybe the beginning of it. If you don't, I think you'll still be okay. But it is helpful to read before. If you can get on a schedule where you're ahead that way, that's really good practice for the rest of your classes.
Okay.
Yeah, but it is winter session. It is a 5-unit class in 5 weeks, so I get it if you don't, you know. Yeah. Any questions, comments, concerns? Sanjita, you have a question? Please feel free.
Hi, I have a question. It's not to do with the content today.
Mm-hmm.
But so I've been trying for a while now to enroll into the spring session of Physics 102. However, I can't get on the wait list either because it says I need to finish the prerequisite for taking Physics 101. So I
Yeah,
didn't know if anyone else had this issue. So
yeah, I'm pretty sure a lot of people have this issue. We did talk about it a little bit yesterday, and it's very specific. So you have to do the prereq clearance form for Physics 102 also, just like you did for Physics 101 if your math doesn't match the numbers at Trade Tech. Yeah, and it's that's exactly it. Saja put it in the chat too, that you would just have to do the prerequisite override. And let me make this announcement also for everyone. Several of you have emailed me about Physics 102 in the spring, and I'm very, very happy to have all of you in Spring Physics 102. And I completely understand that the Physics 102 is full online. Don't you guys worry. We will find a way to get you into the class if you want to. And I will make sure of the last week of class, the fifth week, that we all kind of transfer over together. You know, if that's something that you want, then great. If not, that's okay. But someone has to remind me. Someone has to remind me in the fifth week for us to talk about this. But I'm pretty sure I'll remember because there's so many of you. But it will take a minute. Y'all just have to be kind of patient with me. And let me put in the link in the chat for the stuff that you need. Sanjita, if you could make sure you look at the link in the chat, there's the link for it. Yes, so another question, can we still email you to get added for 102? I'm going to say that you don't need to. You don't need to because the fifth week in class here, we will all talk about it and transfer over together, and I will get a list of all of you guys. But I promise you, you will get into Physics 102, at least in my class, if you want it. Yeah. Oh, I see the link. Thank you, Patricia, for helping. I appreciate that very much. Thank you, Bradley, too, also. Yeah, and you'll definitely remind me. Thank you. Okay, I don't think I have any more specific questions for the content, so I'm gonna stop recording and say that lecture is officially over, but I'm not going anywhere. I'll still be here if you have any questions specific to you. If you have any questions about the material, hang out. Yeah. Okay. I will see you all tomorrow.
Thanks,
10
Professor.
a.m.
Have a great day.
You
Thank
too.
you, Professor.
Bye, guys. Thank you.
Thanks.
Thank you all.
Thank you, Professor. Bye.
Bye, Esmeralda. Thank you. Bye, Saja. Bye, Daniel.
Professor.
Bye. Thank you. Thank you. Oh, what interesting names.
Professor?
Yes, Randy.
Will there be like there was assignments yesterday and I did those. Will there be ones to come now on this section that we're doing now?
Oh,
so
yeah.
I could start on them or?
Yeah, Randy, I totally just said that. I'm gonna publish it. Actually, I'm gonna do it right
Oh,
now.
oh.
Yeah.
Sorry, I didn't.
Well, it's okay. I just published it right now, so refresh your Canvas and you'll see them. And I'm really glad that you're ahead on them.
Okay,
And
thanks. I really appreciate it.
yeah, it's no problem. Nada, I think you have a hand up if you're still here.
Yeah, Professor. I have a question. So first, I
Let me just stop recording, everyone. Again, thank you guys. Thank you all. Yes, and I'll be here. If anyone needs to talk, I'll be here. Let me just stop recording.